this. I believe I made up some different question for you related to this. Let's say, oh, I wish I remember what it was. So probability of, let's say, head and 6, something like that, or not really. So it was one question that I made up related to problem number 3, where you toss a coin and then roll a die, right? So if it's a probability of head, and means times probability to get 6, then you need to simply multiply those probabilities by multiplication rule. And out of 2 possibilities, there is only one head, because the sample space is either head or tail. So there are 2, and I can see 1 out of 2 head. And for the die, out of total of 6, so we have 6 choices, 5 and 6. There is only one that I'm interested in, and that's a 6, so it's 1 out of 6. So when you multiply these 2, you get 1 times 1 on the top is 1, and 2 times 6, 12 is on the bottom. So that's the answer for the quiz question that we had last time. In fact, one may notice if you had head and 5 or head and 4 or whatever, 1 out of these 12 possibilities, it's always going to be 1/12. So it's interesting to observe. So the key part of that section 4 of chapter 3 was to multiply, to follow multiplication rule. I want to also tell you that next week we're going to talk about the midterm, because midterm will be a week after next. So it's in 2 weeks from today, we're going to have a midterm exam. So next week we're going to talk a lot about it in very detail. I'll supply you with a practice midterm so you can see how it's going to look like. So we're going to devote it plenty of time. So please don't worry. So next week we will get into that. This week is kind of messy weather, so you have other things probably to worry about. And this week we just continue with chapter 3, and that's the plan. So today I just want to do more problems in this chapter 3. So let me go to the next page, do some problems here in this section. Looks like we have some more problems. So maybe I can take a look at exercise 21 that has a relation with the table that they have here for us. So this table is dealing with results of pregnancy test. So it says if subject is pregnant, then we can get total of 85 women, and non-pregnant total is 14. So if you add them all together, you're going to get a total number of sample elements, which is 99. So exercise 21 is dealing with selecting 2 subjects. So in this chapter, we start to deal with a repeating experiment more than once. So in exercise 21, they're talking about selecting 2 and finding that probability of getting someone test positive for pregnancy. And turns out the positive for pregnancy is right here. So it's actually 83, right? I say, but they may not be pregnant. Well, the question is test. So they care about the positive test result. So positive test result here. So probability that someone gets positive test result, if that's one person only, is going to be 83 out of 99, right? So if there was one person selected, then 83 out of 99 is a chance the person tests positive. So total is always in denominator, and that's our total number of sample elements, 99. And 83 happen to test positive. Whether they're pregnant or not, we don't really care at this moment. We're just trying to find out the probability someone gets positive test result. Now, the actual exercise 21 wants us to do the following. They want to actually test two people, and turns out that after you test the first person, then you want to select a different, right? Different subject, not the same, because I guess there is no point to test exactly the same subject once again, because we already tested. So you want to test different. So I copy the first one the way it is, and now I use multiplication rule, just like in the previous exercise. And we now have 98, one less subject, because we want to select different. You cannot choose same, so no longer you use 99. One is gone, one less. Out of 98 subjects, how many will test positive? Please notice one of positives is also gone, because that person that tested positive I already calculated in my first step. So there are 82 left. You see that? One less, because again, I selected a different person. I say, well, what if the first one didn't test positive, was negative? So, well, we are not answering the question of this exercise. The question is, they both test positive. So we assume that first did tested positive, period. And once that person was tested positive, we no longer consider that person. So one less is left, and that's why we use 82. So I just follow the question of this exercise. I know different things may happen, but they care for both of them being tested positive. So let me put this in a calculator. Let me clean this mess in here. So we have now 83 divided by 99. Then you put the cursor next to that fraction. So you're gonna multiply it by 82 out of 98. I love this calculator. It clearly shows me everything I enter in it. So the fractions very convenient to work with. And here's my answer, 0.7015 dot, dot, dot. So I put a few significant digits in the calculator, copy them from calculator on my page. That doesn't really take too long, right? So we've got answer for problem 21. So when we repeat our experiment, we multiply, because we do one selection and the other. So and means times. So today I'd like, as usual, to do as many as we can of these exercises to get used to this and means times rule. So we now select only one subject. So it's different. The previous exercise said select two subjects. Now we select only one. So it'd be definitely a different approach. So they still want to know the probability of getting someone who is negative or not pregnant. Okay, negative or not pregnant. I put NP, not pregnant. So we do selection again out of 99 subjects. Remember, the total is still 99 for our sample. So we care about negatives, they're here. And then we care about not pregnants, they're here. So not pregnants, and then negative. So please notice that negative, that's the second column, and not pregnant is a row number 2. So I have to put them all together, all of these numbers, 3 plus 11 plus 5, all of them go here, and the numerator of this fraction, so we end up with something that looks like 19 out of 99. So you can leave this as your answer. Very good that you double check this, thank you. But I will put this in a calculator, just kind of be consistent with all the problems we do here. I think the textbook also puts answers with a calculator, so 0.19191919 dot dot dot. So I can put a couple of 19s and dot dot dot. Okay, so different type of question. Instead of selecting 2, we select only 1. No wonder we're not gonna multiply anything here, but it's just like in the old times, we have one fraction that actually has total in denominator and something in numerator, and that's all we care about. Let's do 23. I like this group of exercises. It's nicely related to the table, and all sample is laid out in front of us. So why don't I do number 33? So it's 5 here erased. So in exercise 23, again, they select 2 different subjects. So we're gonna do and, we're gonna do times again. So what's the probability they're both pregnant? Well, probability that subject is pregnant is taken out of total 99. And now we see that pregnant stands for the first row here. So it's 85, right? Some of them tests did not identify, some did. Well, the test is not perfect. Test sometimes tricks people, but it helps, I guess, in some ways, right? So it's better than nothing, but looks like that only first row is what they care right now. So if we selected 1, probably I put PR, so pregnant, so we better see this. Pregnant. Now I need to select another subject, so that'd be a probability that another woman is pregnant, looks like, right? Well, so let us multiply. I already know what the first one looks like. It's 85 out of 99. Now things changed again because the total was, this is a total was 99, the grand total here. So we need to again select different, so cannot choose the same. So we need to change this, actually not here, but in the other one. And here I changed to 98, right? And analogously, the total number of pregnants will be 1 less, 84. So it looks like the pattern is pretty clear. So we just drop by 1, right? And numerator and denominator. And that's how we produce our little fractions. And of course, for this one, I don't want to do the algebra by hand. I just want to use a calculator. So let us use it. So someone here. So it looks like we need to enter a product of two fractions. 85 divided by 99 is the first, times another fraction. 84 again is divided by 98. Okay, so there is some answer. I put it down: 7, 3, 5, 9, dot, 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 8. Just put dot, dot, dot. So this way you don't have to round. So I put a few digits, and that should be good enough. Okay, so turns out this story is actually called conditional probability, because the condition that our sample changes when you select the second person is imposed. And that's actually the story of section 3.5, because multiplication rule and conditional probability is the name of that section. So I would say that 3.5 is here, and 3.4. I don't see any difference in between of 3.4 and 3.5. In fact, here, look at this example. We have the same exact table. Maybe I can look at the exercises related to it, since we're already familiar with the information on that sample. So let us check it out again. So what do they want here? They have selected 1 out of 99 subjects, and they want to find the person test positive given the person was pregnant. So they gave us only pregnant ones. So not pregnant are not considered. So they gave us that we have 85 women to consider. So I put this in denominator, 85. And say, what about 99? I remember the total was 99. Not any longer. When they say word given, it means you're not considering the whole sample. They gave you that they just shrink the sample to pregnant only. So we no longer deal with 99, but with 85. So they shrink the sample, so your denominator shrinks. And now there are two possibilities. The pregnant could be either tested positive or negative. So they want to know probability that test positive. Okay, that's 80 tested positive out of 85. So here's the answer. So notice that once you shrink in your sample, then your denominator is different. So you no longer care for the other part. So actually for the rest, so well, you get some kind of fraction. The second part has very similar question, but it is not the same. You can compare what they ask in here with what we found in the first part. Notice they switched. They given that it's positive test result. So they used to give you that there was a pregnant subject. Now they give you different number. They give you positive test results. And that's the reason why you can see denominator is changed. It's 83. Because we no longer care for the negatives. So the whole problem totally different. And now among these 83 positive test results, we need to see how many are actually pregnant. And well, 80 are pregnant, so 80 out of 83 is right here. So the point of this whole story is that whatever is given, that's your sample size. So they usually don't give you the entire sample. They concentrate only on a part of it. So I think that's a nice example here in the table, and then it's nicely solved in the beginning of section. So we can definitely take a look at it. And I'd like to look at problems that start at exercises here on the practice problems. So I'll start with exercise number 7 that definitely needs some cleaning here. So exercise number 7 that talks about probability of at least 1. Turns out this is a very standard type of question because at least 1 appears, I think, everywhere on this entire page. So this at least 1 is actually what we want to concentrate on today. So how about problem number 7 that says find the probability of at least 1. And it turns out that at least 1 we always approach with a complement. We subtract from 1 the opposite to at least 1 means to have none of them. Let's see what this means. In this exercise, they talking about 5 children. So for 5 children, if I'm interested in getting at least 1 girl, it means that we can consider the case that we have 1 girl. That's at least one or more. Or more, so it could be 2 girls, or 3 girls, or 4 girls, or all 5 girls. You see how many possibilities are covered in a statement that the couple has at least 1 girl. 5 different ones, so we need to consider all of them. And the complement to this will be no girls, which means all 5 are boys, right? And it turns out there is only one possibilities that we can actually consider then, probability that we have no girl, so you can say like no girl, remember we used to write complements with a little bar, and no girl, and another no girl, right? So 5 times boy, or no girls at all, so it means 5, like with a bar, right? So what's the probability of that? And this one I can definitely calculate right away because I know that probability of no girl means probability of boy, so it's 1 out of 2, right? Either girl or a boy are genders of children, so out of 2 genders, only 1 is going to be not a girl, so 1/2 is probability, and 1/2, and 1/2, and means times. That's what we are already learning in here. So all of that will be 1/2 raised to the power of 5. So I can subtract from number 1, 1/2 to the 5th power, just like that, and I'll get the answer. So the point is, I don't need to go through the 5 possibilities and calculate all of those probabilities together. I just go with a complement, so it's a probability of a boy, and then I subtract it from 1 and get my result. So let me subtract from 1, 1/2, where I can say 0.5 raised to the power of 5, right? So you can just use 0.5 for convenience to enter in the calculator, or you can put 1/2 in the parentheses, same thing, doesn't matter. So it's 96875, and this is it. I say, Alex, what if I round? What if I put 9 0.6 or 0.9. Well, if you put 0.9, you need to round it be 1, right? So it's not really a good idea to round it so badly. So that's why this textbook actually wants you to keep a few significant digits, so a few decimals. Put 3, 4. How long does it take you to put 3 little digits? Like less than 1 second, I'm sure. If you just get your pen and write a few digits, it just doesn't take time. So put this down, because this way the answer makes much, much more sense, of course. So just practice. And I also do this in all the exercises. I'm sure you already noticed that. So let's do more. Looks like probability of at least 1 repeats throughout these exercises again and again. So how about problem like 15 here? Number 15 talks about the alarm clocks. So if the alarm clocks don't work, well, that's disappointing. So we can actually try number 15 here. And it says that 99% the chance that alarm clock works. Okay, so I can write that probability that the clock works is 99%. Well, we always turn this to decimals, so it's 0.99, right? 99%, 99 hundredths, 0.99. Look at their question. Same thing again. What is the probability that at least 1 works correctly? So if somebody wants to wake up, the probability to wake up will be at least 1 works. Well, at least 1 works. Somebody wakes up. 2 works, 2 work, or 3 work. The person wakes up. That's exactly why they wanted to do this. But the opposite to it will be none of them worked. So none of the alarm clocks work. So the person overslept. That's disappointing, because someone was actually using 3 alarm clocks. So at least 1 means 1 works, or 2 work, or all 3 work. And that's the way the person wakes up, but none of them work. 0 working alarm clocks means that person overslept. And that's what none really stands for. So I try to find a probability that first didn't work, and means times, second didn't work, times the third didn't work. That's what none of them worked means. And this is very similar to the previous exercise. It's actually the same procedure, but there we had 5 girls, and here we have 3 alarm clocks. So here's a little bit less to work with. But first step, we need to find the probability that the alarm clock actually fails to work. And that's the opposite to the fact that it works. So it's a complement, which is remaining 1%. 99% that it works. Well, remaining 1%, it doesn't, right? So 99, and the complement is just 1. Okay, so let us multiply 0.01 by another 0.01, and again by another 0.01. Well, this is going to be a third power of 0.01, 0.01 cubed, right? So this is what I have to subtract from 1, 0.01 to the power of 3. And I will again use my calculator. So you should get used to the calculator. If you lost track where it is and how to get to it, I'll put this in the link to this calculator in the Zoom chat. So please save it. It's there in the chat. You can see the calculator and try to use it, because in this section you will need the calculator, as well as in the following chapters you will need it even more than in these sections. So I just produced the answer. It's a bunch of nines. 9, 9, 9, 9. So is it better? Is it higher chance? The answer is of course, because you used to have 99% of a chance to wake up with this alarm clock. Now it's 99.999. So it's very, very close to 100%. So instead of 99%, you pretty much gained yourself almost 100%. So that's one of the highest possible chances. So that's great that one could have such a big chance to wake up. So at least story continues in here, and you could just do more and more of them. And I think that instead of giving you a quiz today, I will do another problem. I think that'd be a good idea, because problems looks like are a little bit longer, even though they're of the same kind. The process is the same, but I think it's good that you get used to this procedures a little by little. So I'm looking at exercise number 17 here that says using composite blood samples. So they mix blood samples in the lab in order to do the test, I guess, to save the money. So it says it's less expensive this way. So they combine the samples and they say if everyone is negative, the test is negative. So in exercise number 17, they want to make sure that, well, if everybody tests negative, then you keep adding those samples, mix them together, the whole thing is negative. There is no positive, everything is negative. Looks like, but one can say, what if there be a positive? So they test 3 people, and the question is, find the probability that the result of the mixture is a positive. Well, how positive is possible? If at least one is positive, you see that they just keep giving you the same exact question again and again. At least one is positive. So it's just like here was working. So if there are 3 people, so there's 1 exactly positive or 2 exactly positive, so all 3 are positive, then the whole thing will be positive. So what's the probability of that? Well, you already know that it's a complement to probability that all of them are negatives. All 3 are negatives. So if I subtract it from 1, because that's a complement, I'll have not all of them are negatives, the opposite. All negatives, the opposite are not all negatives. So somebody is positive, at least 1, maybe 2, we don't know, but what's the chance of this? Well, probability that all negative will means that all 3 are negative, means that first is negative, and means times second is negative, and again times the third is negative. So it looks like it'll be a probability of negative raised to the power of 3. And you say that same footsteps as the previous exercise. So they give you probability of positive. Let me get a little bit of room for this. So probability of positive is 0.1 or 10%. Okay, so let me write this down. So probability of positive is 0.1, I need right now probability of negative, so that'd be its complement. So it's 1 minus 0.1, which is 0.9, 90% for negative. So 0.9 we times with another 0.9, right? And again with another 0.9, we times it 3 times with 0.9. So I get 0.9 to the power of 3. Great. So let us get the answer. It's 1 minus 0.9 cubed. So it looks like we just get this 1 minus, and then there is some kind of power that we utilize throughout pretty much every exercise in this section so far. So let me do this again. Let me clean this a little bit. So notice that above, I had a couple of times already entered this 1 minus 0.9, right? So it's not positive, and raised to the power of 3, like that, right? So we have for the negative, all 3 of them will be found 0.9 cubed, but at least one positive. It's about 27%, 0.27. So I guess we got the idea of this, at least one. We never want to approach it directly, because otherwise you would have to calculate probability of exactly 1 or exactly 2 or exactly 3. And when you start to calculate the chance that this is exactly 1, it could be 1 first and 2 others positive, actually exactly 1 positive. So it'll be just 1 positive, not negative. So let me get this idea for you so you can see how tedious it's going to be. That's why you don't want to get to it. So positive could be first, 2 negatives, or positive could be second, or positive could be a third. You see, there are already 3 possibilities for 1 positive. And then for 2 positives, then you're going to have first 2 positives and then negative 1. You say, oh, that's a nightmare, Alex. There's so much. Yeah, there are lots of possibilities. Turns out 3 more. And that's for 2 positives, 2 pluses, 2 positives. And all 3 positives, well, that's easier. There's just plus, plus, and plus. But you have to get all of these 3, actually 3, 3, and 1 more calculated. But it's much more straightforward to calculate it like that. Well, it turns out that in the next chapter, we're actually going to see how to calculate those directly with a formula. I just don't want to get into this right now because it's really going to be a little bit offline. But the message here is that it's so much better to use a complement. I hope it's clear enough. So we worked on section 3.5 today, and also 3.4 a little bit. So I guess